The voltage regulator adjusts alternator output by controlling the amount of current it sends to the field winding in the alternator. These regulators are now controlled by the vehicle's ECM in response to actual and expected system loads. An alternator regulator will limit voltage output by controlling the rotor's field current, whereby output voltage is directly related to field strength and rotor speed. An increase in either factor increases voltage output. Likewise, a decrease in either reduces voltage output. Rotor speed is governed by the engine's crankshaft and cannot be altered to simply control the vehicle's alternator. But altering the field current in the rotor winding electronically allows us to control the alternator's output. At low rotor speeds, the field current is commanded by the voltage regulator to full strength, while at higher rotor speeds, the field current is reduced to enable a relatively stable voltage output. We are all reasonably familiar with the location of solid-state regulators. We see them mounted on the alternator case or inside its housing. They're compact, have no moving parts, and are not seriously affected by temperature changes. But have you ever wondered how they work? Early solid-state designs combined transistors, thymistors and xenodiodes to control the rotor field. Newer designs use an integrated circuit for control and feedback, with commands sent by the engine control module. Because of their construction, however, all solid-state regulators are non-serviceable and must be replaced if defective. A xenodiode is designed to act as a one-way electrical check valve until a specific reverse voltage level is reached. At this point, the xenodiode allows reverse current to pass through it. The electrical resistance of a thermistor changes as its temperature changes. It is used to ensure correct battery charging voltage in all operating conditions. Some manufacturers use a capacitor in order to smooth out any voltage surges or spikes and protect the regulator from damage. Let's look at the operation of a typical voltage regulator circuit inside an alternator. With the ignition turned on, current flows through resistor R1 and diode 1, then via the base of transistor TR1, finishing at ground. This causes the transistor to allow a ground path for the rotor winding through its emitter collector circuit. Since the alternator lamp has positive voltage supply on one side and a ground path on the other, it will illuminate. Voltage supply for the rotor is by the ignition circuit through the L terminal junction. We can see that diode 3 blocks this current from flowing to ground via TR1. Once the engine is started and the alternator stator begins to produce energy, a diode trio connected in parallel with the rectifier bridge supplies DC current to the L terminal junction. Since there is now positive current on both sides of the charging lamp, it turns off. The F terminal is connected to battery positive, with discharge limited by the high resistance of R2 and R3. This circuit allows the regulator to sense the current battery voltage levels. When the battery voltage level reaches the manufacturer's predetermined set point, the measured value between R2 and R3 is high enough to cause the xenodiode D2 to conduct in reverse bias. Since transistor TR2 now has a voltage source at its base, a path is opened through its emitter collector to ground. This has the effect of shorting or pulling the voltage from the base of TR1 from high to low, effectively turning this transistor off. With TR1 off, there is no ground circuit for the rotor, so the magnetic flux within the field coil begins to decay. At this point, the output of the stator is dramatically reduced, resulting in a lower output voltage at B positive. This voltage reduction has a knock-on effect towards the regulator F terminal, and therefore the xenodiode D2. When voltage drops low enough, reverse bias of the xenodiode is prevented, stopping current flow to the base of TR2, effectively turning it off. The base of TR1 is pulled high, completing the ground path for the rotor, and so the field current and system voltage increase once again. This cycle repeats many times per second, limiting peak alternator output voltage. There are other components in the regulator that perform necessary tasks, like the capacitor C1. It provides a stable voltage across resistor R3, while resistor R4 prevents excessive current through TR1 at high temperatures. Resistor R2 is a thermistor, which causes the regulated voltage to vary with ambient temperature fluctuations. R5 provides the indicator lamp with a ground path, allowing it to turn off if the field circuit is open. The days of internal and external voltage regulators are long behind us, with most manufacturers now opting for ECM-controlled charging systems. The voltage regulator has been replaced with a field current control unit, which is operated by the ECM. These systems use a high current transistor within the unit to control the rotor field coil magnetic strength. Based on input parameters like battery state of charge, coolant temperature, ambient air temperature, battery load, and which charge cycle the vehicle has chosen, the ECM will send a pulse width signal to the field control unit to alter rotor field strength. This PWM control will always change based on the needs of the vehicle's electrical system. This PWM is delivered to the field control unit's L terminal where it is processed. The logic circuit can then operate the field coil driver to achieve the ECM's desired output. Voltage output is sensed via the diode trio and fed into the logic circuit for evaluation. The unit converts this value into a duty cycle feedback signal at the F terminal. The ECM then interprets this value as a voltage output from the alternator. If the value is too high or too low for the selected charging program, the ECM will adjust its PWM control to the L terminal. This cycle is repeated until the engine is switched off, or the ECM has decided it does not require the alternator to provide any current to the battery or the vehicle's electrical system. ECM-controlled alternators allow the charging system to be monitored for faults and record them for later diagnosis by the technician. They also allow for more precise management of the battery and charging system by operating when and as required by the vehicle. We may need to diagnose and replace a voltage regulator or field control unit at some point of our career, and system knowledge will help us make the right decisions when doing so. Keep training. Thanks for watching.